So here's our problem 2 in homework 7. I don't know if I'll have enough time for a class because it's 8 after, and I like to go to class early, so maybe I don't want to do this. I'll just pause the video and come back to it if I need to. Alright, so we have this small cart right here that's got this 4 kilograms, and I'm pointing to the thing. You can't see my hand. Okay, and with frictionless wheels, and it's on this rounded slope. And it's attached to the cylinder over here that's 0.6 kilograms with a rope that doesn't stretch, and the pulleys aren't frictionless or and they're massless. Therefore, that message just tells us the tension is the same everywhere. It wouldn't be if they had the pulleys had mass or had friction. And this angle right here is 30 degrees, and the cable is tangent at this moment to this slope, and that slope has a radius of 1.75 meters, and the cylinder is traveling upwards at 1.2 meters per second. We want to find the acceleration of the cart, find the tension in the cable, and find the maximum speed that the cylinder can go for the cart to remain in contact. So I've written the problem out again, and just as briefly as I think is necessary. And I want to try to start out maybe, I'm going to go ahead and figure out what the dependent motion relations are. So here we go, and we'll call, I wish I had called these A and B instead. So maybe I'm going to continue with A and B. I usually think as 1 and 2 being designated for different times. This is all in an instant, so I might switch over to A's and B's. So I'm going to call this one, let's call this YB, and we'll go down that way. And then I guess I could use an arbitrary one, but I went ahead and go from right there, and we'll say that this distance right here is going to be, I'm going to call it S because it's not like related to anything, and I'll call it SA right in there. So we write out the length of the thing, and we note that we're going to have 2YB plus SA, and so we take the derivative of them, and we have 2VB plus VA. Therefore, let's say VA is equal to 2 times VB. And then to acceleration, and there's the acceleration, whoop, that was supposed to be B, there you go, and the A. So we have the acceleration of A is equal to 2 times the acceleration of B. Alright, just get that out of the way. So there's a kinematic relationship. Even though we're doing kinetics, we still need to know kinematic stuff. Can't get away from it. So let's go here, and we need to do 2 separate sets of FBD IBDs, one for this and one for here. There's 2 separate motions taking place. So let's do the cart FBD first. Over here, a FBD IBD, and didn't do a very good job of making that a nice rectangle. And I didn't put them like side by side with each other. I used to do all of my solutions in Word documents, and with little figures I would make using simple images combined together. And I kind of like that because I could reuse them and they look perfect. Oh, you couldn't see me doing it. Yeah, it was boring, wasn't it? That was boring. You couldn't see me doing it. All right, so we have the weight of this, but without mg. I have to be careful with the angles right here. They gave us, for some reason, they gave us this angle. What do you say we just go ahead and change this to this angle instead? I like that one better, right? Let's call it theta. We didn't use theta for anything else. They decided to go beta, and they decided to make it measured from vertical. I like measuring from horizontal. It just keeps it nice, right? And although, like right here, actually, this thing right here is actually, that would be the complementary angle. So okay, maybe we'll keep it that way. Okay, so we're going to put the normal force in here. Fn is going to be right up against there. Is there any other forces? Yeah, sure is. There's going to be a cable tension. Whoop. Ft, that's the thing that keeps these things together. Now, we expect there to be an acceleration in the tangential direction. Yes. All right, so let's align these right here. Well, let's draw the coordinate. Let's do the coordinate axis this way. Okay, here you go. So we have ET, and here's EN, right? Because they're saying the cable is tangent to the thing. That's a little. So we have mass times acceleration in the tangential direction. Oh, and we might want to designate this AA. Do I want to say T? Yeah, kinda. Yeah, I guess I do. I want to go tangential, and then we're going to go M, acceleration of A in the normal direction. Yes. I think that makes sense. Do I want to write out the equations over here or put the other figure? I'm going to put the other figure over here. So I'm going to go FBD and IBD. And in this case right here, good old X and Y are going to be fine. I don't know why I didn't use unit vectors there, but I hadn't before, so I'm not going to do it now. So let me put this guy in here. And quite a trick to often do, let me see, I'll make this smaller here, is to include the pulley right there. So I'm going to draw it kind of small. I'll get this out. I started trying to be a little neater. I don't know. We'll make it right there. There you go. Anyway, we have this and this. So we're going to have 2 times Ft. It's going to take place right there. We also have, I forgot over here when we did M. Let me fix my M's. Got to be careful because we might write these equations out and get them confused. So if you've been following along perfectly with this, you're going to have to erase your things. Okay, this is MA, and this is MA, and this is MA. So this is going to be MBG, right? And we don't necessarily know the direction of this acceleration, by the way. We just know the direction of the velocity. We know the velocity is going upwards, but it could be slowing down. So that's kind of a thing to consider. So I think I want these to match, and then if I get a negative answer for that acceleration and that acceleration, right? So this is coming down, so this goes down. I call this, what I do here, is guess with agreement, right? So we're going to go the mass of B and the acceleration of B. Now, we're going to keep in mind, when we did this acceleration here, this acceleration is the tangential one, right? So this is the acceleration. This is this guy. This guy is just about changing direction, but this one is going to coincide with this one. So that's the thing. These things are linked by way of this, and they're also linked by way of this tension. So you want to kind of keep the big picture in mind as we're going through here. Now we can write a bunch of equations, and hopefully we're going to be able to narrow it down so there's only one unknown. And I think we're going to be able to do that. And one thing we might find out is, I'm double checking on something. I think it's because we're going to know this is going to let us find in the normal direction. So I don't know if that's going to help me any. I got to decide on that because there's no friction in there. If there's friction in there, we might need to know this. There's no friction in there in that direction. Trying to think if there's anything that's linking those two things together. Like I said, I haven't solved this problem. So I might actually pause the video because it's almost time to go to class. And then I might write something out over to the side just to see, just to double check and see what the gimmick is right in here. Do I want to do any more? Maybe I'll write a little bit more in here. I got 2 minutes. Let's see about my angles. This angle right here, I happen to know that's the same as beta. Right? Is that true? Let's take a look back over here. Yeah, see, because you go right there, and you go right, so it's got to be the same angle for sure. So I'm going to see if, I don't know if I'm going to need this guy right here, but I could go sum of the forces in the normal direction equals mass times acceleration in the normal direction. Something I might want to also see, they already told me these velocities, so I can actually do this one up here. I can say the velocity of A at this instant is going to be 2 times the velocity of B at 1.2, so I can equal to 2.4 meters per second is what the velocity of A at this moment is, given by this guy right up there. So when I get down to here, we know that's going to be the velocity of A squared over rho. That's the reason why they gave us that thing. Let's see, look at the this right in here. So like my phone is beeping and telling me it's time to go. So the normal direction is positive that way according to how we've drawn our axis. So we'll say a negative Fn, right? And then we're going to have a positive MA G, but times the cosine of beta. And the tension doesn't fall into there, so we're okay here. And we're going to have that, it's going to be equal to, oh, you know why this is going to happen? I know. This is going to help us with part C. I don't think we're going to need it for part A and part B. But as I try to describe to you, this is our process right there. This thought process. Sometimes we have to think about what we're doing here. So we have the VA squared over, and we can write, here's the generic formula right here, but now we can use the specific right here. So this is capital R from what they gave us right there. So this might be useful to us later on. So we'll maybe like put a pin in it, call it equation 1 for something that we might want to use. But you could see that we'll be able to figure out what Fn is going to be based on this. But we don't need Fn for anything. We know this, we know that, we know this, we know this, we know this. We'll be able to figure out Fn, but then we don't do anything with it because there's no friction onto this thing. But if there were, this would be what we would use to be able to have that that friction force if we were to place it on there. So that's just like a good to know. So let's do the sum of the forces in the tangential direction equals mass times acceleration in the tangential direction. And of course that's going to be this way on this. So we're going to have a negative MAG, and it's going to be the sine of beta. And then we're going to have the tension, and that's really the thing that links these two together, is going to be equal to mass of A times the acceleration of A. Which way we could just call it MA, acceleration. But let me keep going and say that it's the tangent right in there. All right, so we could put some values in there. The thing that we don't know this, and we don't know that, right? So, but we can relate them. So we could go ahead and put things into here. Numbers into there is 9.81 to the sine of 30 degrees plus Ft is equal to 0.4 times the acceleration of A in the tangential direction. And I really do got to go because it's I got a couple of minutes left. So there we go. Let me pause this. I've paused it before for a long time. It's already 15 minutes into the thing. It's going to be a long problem. Anyway, we'll see. I'm going to go see you guys right now, and then I'll come back. Okay, I'm back. I know. That was fun. It's almost as if no time has passed. Oh, let's see, where were we? I think we were trying to figure out what the tension was, but we don't know the tension because we need to go over to this other FBD, IBD. But we can like solve for tension right here. So let me go ahead and do that. So I'm going to get 0.4 times 9.81 and 30 sine times, okay, so that's that thing, and so that's going to go over to the other side here, and we get 1.962 plus 0.4 acceleration right here. And we know that this acceleration is related, can be related to this acceleration by way of this right here. It's just going to be 2. So we can, when we get to a point down over here where we have the thing in terms of tension, we're going to be able to combine it with this. That's our strategy. So we take the sum of the forces in the y direction is equal to mass times acceleration in the y direction. And something I want to make sure that we emphasize is you could be tempted to think that the acceleration is downwards and is equal to gravity, but that's not where that goes, right? Gravity always goes on the left-hand side because it's a body force, the force of the Earth pulling down on things. So we have 2ft minus mbg. It's going to be equal to mb times ab. So we can put in for the limited amount that we have here. This is going to be, where did we go up here? It's going to be 0.6 times 9.81 equal to 0.6 times AB. So we can go ahead and stick FT over to here. So 0.6, 9.81 times, and divide that by 2. Right? So we can put that over here onto this side. That's going to be 2.943, and that's going to be plus 8.3 because we're dividing this by 2 right over there, AB. Right? So we might want to call this equation 2, and we'll call this equation 3, and we're going to go combine 2 and 3. If you haven't noticed, I do this in a lot of homework problems where I'll just to try to organize myself. I mean, it's not only is it communicating to the professor what you're doing, but it's also kind of just kind of keeping to yourself. I might also have wanted to call this something, and because I didn't start out calling it a number, I'm going to call that 4. So we have 1, 2, 3, and 4 right up there. So let's say 1.962 plus 0.4. And who am I trying to solve for? I want to try to find the acceleration of 1, right? So that turns out to be A. So I'm going to do it in terms of A. Here, let me move this keyboard over to the side so I can move the paper up. And so I'm going to keep this right here, but I'm just going to keep it calling it A right there. And that's going to be equal to, so I'm setting this equal to that, right? So now I can go into 2.943 plus 0.3 times, and that's going to be 1/2 or 0.5 acceleration of A, right? And I want to be clear here. I don't need to go over here. This should actually be a negative, just so you know, like it should be like actually negative right in there, technically speaking. But I've already established my directions by way of this, what I've drawn right here. So I don't need to enter this as an equation. I could have just as easily, and I often like to do this instead, put that in right there, just to say the absolute value, we know the magnitudes. Because I've established my directions with this. If I was going to play the sign convention game, I might have chosen this is going that way. I don't know. It's something along those ways. But I think it's better to just move along this way. We have a dependent motion, and we know that the things are going like opposite. When this one goes up, when that one goes down, that kind of thing. So let's see, I can find what this is going to be, right? I could take the, okay, so I have that 0.35, 0.3 and a 0.5, 0.3 and 0.5, and should that be 0.15? Okay, so that's going to come over there, and I'm going to subtract that from the 0.4, all right? So it ends up being 2.5, and then I'm going to subtract this one over here. So I'm going to take this and 1.962, subtract it from there, and then I can divide. So continuing on, this is 2 continued. And I have a couple minutes until my next class. Don't you just love Tuesdays and Thursdays? Yes. I think for this, we had this relation, as you'll recall, Fn plus mag cosine of beta equals ma fa squared over r. Now the question says, from the original question, let's take a look at it, make sure we're looking at it, and there we go. It says the maximum speed of the cylinder, this guy, for the cart to remain in contact. Well, we can figure out if it remains in contact. That's the same thing as saying that it's almost not in contact, right? So when we have that kind of problem, and the only way that you would know this is to have some little experience with it, would be like, just like the Dukes of Hazzard car in the example, the normal force goes away, just on the verge of going away. So when we set this equal to 0, we could find the velocity when that's going to occur, at least at A. And then we could figure out, go backwards with this, and figure out the velocity at B. So if we go, I'll write it out, Fn plus mag times the cosine of beta equals ma va squared over capital R. And goes to 0 when just losing contact. When that happens, we're in this situation, and we'll also notice that the mass will cancel out. It's like a weird thing that happens. So we got 9.81. Yeah, I know what you're telling me. All right, here, let's dismiss you. 9.81 times the cosine of 30 degrees equals VA squared over, and the radius of this thing is 1.75. So we can find that VA for that. So we get 9.81, 30 degrees cosine times it, times 1.75 times it, and then take the square root, and we get 3.856 meters per second. But we want VB, and VB is equal to 1/2 VA. So 1/2 of 3.856 is 1.928 meters per second. All right, so let's write down the answers. Actually, first, maybe I should check and see if this agrees with the source material. I don't have the right answer. What do you mean I don't have the right answer? How dare you? From here, I think I made the tension the wrong direction. This is the positive direction right here, so I needed to make this negative right there. Yeah. I said that was positive, but I should make tension, I should make that right there should be positive. And because I have that as positive, right? So this should be, tension should be negative here. And this thing should be positive right here. Okay, so that's going to like reverse a lot of the things that went wrong. So if you have just been transcribing this, you're very annoyed with me right now. But hey, I'm showing all my flaws, right? So that's positive right there. I think I got that right. So when I go and I bring this guy, I bring him over to this side, I believe that's going to make this negative. Let me double check that. So this is it. Yeah, I believe that's going to be negative right there. Okay. And I think I got everything up here correct. So when I come back down to this one right here, that should be negative. And whoops, I think my keyboard's, let me move this thing all the way down. Alright, so I made that one negative right there. And so let's see, that's going to change this value right here. It's also going to change this value right there. And I believe it's going to change this value, which is going to change that value. That's why I do things in pencil, right? Okay. And so we set that there. So I'm going to bring, maybe I'm going to bring this one over to that side. No, I'm going to bring this one over to that side. Ready? I'm a little concerned now that I'm going to get a negative value for something. This is concerning here. Let me double check this again. Okay, got it. Damn. Alright, so here it is. Sorry about all the mess of this, but I was correct. I was correct here. The things I corrected, this should be negative, right? And that's negative, and I do get a negative answer. So if I take, I'll take this and I'll subtract it over to the side. So if I take 1.962 and I subtract 2.943 and I subtract from there, I get a negative 0.981. And then I take this 0.4 over to here, so 0.4 and 0.3 and 0.5 times, and then I add them together. I get 0.55, and then if I divide it, I get a negative 1.784. That's because it's decreasing its speed. It's slowing down at that point. It makes sense, right? So if I put that back up into this second equation right up here, which I know that should be negative, and I get a negative right here, 1.784, right? So I go 0.4 times that, and this switches to a positive 1.962, and I add it in there. We get a tension of 2.675. Okay, so I found my mistake. And I believe I will get the same answers as had been in there. Yeah, they got 2.68 and I get there. Okay, cool. So here is, that's part B, right? Part A was, well, part A was this right here. Oh no, I guess, no, we needed, they were looking for, yeah, they were looking for 1, yeah. They were looking for A1, which is this guy right there, so that's the reason why we solved for it, and we got that it's negative there. So let's write down, and we did part B already, so here's the answers. So this was a terrible video, but what are you going to do? See, how did they phrase the original problem, by the way? Let's take a look at the original problem. It says the acceleration of the cart. So acceleration of the cart. So if we're gonna have the acceleration of the cart, that's going to be, and in the beginning we call it 1, so we're going to go back to that 1 right in there. So we'll go back to calling that 1. It's going to have 2 parts. One of it is going to be the acceleration here is a negative, well, yeah, negative 1.784 ET plus, and did we ever find that value when coming out here? Yeah, we must have. We must have up here. Oh, no, we never did. So we can go to the acceleration, the normal acceleration. Maybe I should do it. Acceleration of A in the normal direction is VA squared over R, or we should say that it's going to be 3.8 56 squared over 1.75. So let's see if I can squeeze that in there. 3.856 squared 1.75 divided. So we get 8.496 meters per second squared. So we could write this 8.496 EN meters per second squared. And we could turn that into I and J if we wanted to. Or we could just get this out of magnitude and then figure out what the angle is. But I'm going to leave it where it is, because I'm tired. And I'll be lenient with whatever you happen to turn the thing in there. So the tension in the thing is 2.6, call it 8 newtons. Don't put an arrow next to that because it's a rope, right? So whatever side we cut of the thing would decide what direction that's going to go into there. We could just put it at its tension because you can't push rope. It's kind of implied. And then V1 max to stay on the thing was 3 point, whoops, I just messed up. That's the maximum velocity right there, right? That's not the actual velocity. The actual velocity of the thing should be this right here, right? We never go farther. Oh, there it is. 2.4, right? 2.4. 2.4 squared 1.75. Right. There you go. 3.291. So 3.291 in the normal direction. And this is 3.8, call it 6 meters per second. Wow. This was shit. I would hit an unlike. Hit unlike right here on this video. It just, I disliked it. This was the worst one yet. Well, at least we know where the floor is, or maybe we could try to get to the bottom. So, thank you for your patience in our extremely long video. Maybe somebody learned something. Maybe. I could cut all this shit out, couldn't I? Nah. Just gonna leave it.